Hello, my name is Maria Wimmer.
And my name is David Major.
And we welcome you to our presentation about the visual interpretation of AI decisions. We are part of the biomedical image informatics research team at VRVis in Vienna, and we develop both classic machine learning and artificial intelligence-based methodology for the efficient access to information which is encoded in biomedical and industrial image data. We provide a wide range of solutions and prototypes which always work transparently for end users and aim to support them in their daily work. In the following, we present our work on the interpretation of deep learning-based classification system. We will focus the talk today on mammography classification, which was the basis for two of our contributions, which were presented at main conferences this year. The recent success of artificial intelligence, especially deep learning methods, has driven a surge in computer-assisted prediction for medicine and biology. By categorizing images into classes like pathological and healthy, these methods are capable of relating semantic context. However, the network's output must be handled with care. In a typical inference setup, we input some images into a network, which in return respond with some probability-like values. Here on the right shown for mammography images. But these values are all the information the end user gets, and therefore several questions arise. Are the values actually informative enough? Do they comply with the intuition of the clinical experts so that they can correctly interpret them? Are the values sufficient to check if the output of the network is causally related with the underlying pathology? In clinical practice, radiologists pinpoint and describe a specific region on a radiograph to back their findings. Thereby, they provide a comprehensible interpretation of their work. Neural networks, on the other hand, do not induce a canonical mapping between the prediction and the input image. So the question is, can we approximate this mapping? Or in other words, can we attribute the regions in an image which are responsible for the network output? This would mimic, in a way, how radiologists work. To answer these questions, we propose the combination of a state-of-the-art artificial neural network and an additional interpretation module. By this, we can leverage the accuracy of leading classification systems without losing the needed transparency, crucial for critical applications. In the following, we present this approach systematically, starting with the classifier itself. Given a set of mammography images, we seek for a deep learning-based model which predicts whether there is any mass in an image or not. Mammographic masses are small lumps, which can be indicators for breast cancer. As classifier, we utilize a so-called mobile net. This deep learning model was initially introduced for mobile vision applications. One major benefit of this architecture is that it's very lightweight in terms of the number of parameters. This is due to the fact of efficient use of different kinds of convolutions. The general architecture of a mobile net classifier looks like this. It consists of standard convolution layers and so-called depth-wise separable convolutions. They are organized as blocks and are sequences of depth-wise and block-wise convolution layers with intermediate batch norm and ReLU activations. Overall, the network consists of 13 such blocks, followed by global average pooling and dropout before the final network output. We train this classifier on public mammography data. We utilize two different data sets, one which comprises healthy images and the second one with benign or malignant masses. You can see two sample images on the right. One image, the left one, is from a patient which is healthy, and the left one shows a patient with a mass. We then train the classifier in two steps. First, we pre-train the network on patch level to distinguish between normal breast tissue and masses. We then fine-tune this model on image level for the same tasks. Additionally, we augment images to further increase the generalization capability of the network and apply different learning rate strategies to further increase the generalization capability. The final image classification model achieves an area under the curve score of 0.91 on unseen test data.
As next, let's take a look at our contribution by the interpretation framework. A plethora of approaches have been presented addressing the problem of classifier decision visualization. They can be partitioned into two classes, direct and reference-based approaches. Where direct approaches utilize the assumed analytic nature of a network, reference-based methods study image regions influenced by counterfactual reasoning and analyze how the prediction changes if the region's information would be missing. However, both fall short when introduced into radiology workflows directly. Direct approaches typically yield coarse and imprecise results. It is shown for mammography on the bottom left. Reference-based approaches usually utilize heuristic methodology for information marginalization. As an example for marginalization, we demonstrate established methods such as neighborhood condition sampling and the very popular Gaussian blurring on mammography tissue. As shown on the bottom right, the results should not be considered anatomically sound. We came up with a new reference-based approach which estimates the salient image region of a given classifier by constructing counterfactual evidence using image marginalization in a domain-aware manner. We start with a pathological image and a regular grid binary mask called attribution. Successively, we overlay those two images and generate a masked image. The image marginalization then replaces the masked places by healthy texture and yields the last marginalized image. The goal here is to transform the attribution mask into a pattern that matches the pathology of the image. This can be formulated as an optimization problem by stochastic gradient descent. We derive classification scores of the original image and the marginalized image and compute their difference. Additionally, we derive some mask quality measures and combine those with the classification scores to an optimizable score. During the optimization iterations, the mask becomes more and more focused around the mask region as visible on the images. After a predefined number of iterations, a final attribution result is compiled. We can further improve upon this concept by replacing the time-consuming iterative optimization through the utilization of a dedicated neural network. As visible in the middle, we developed a unit-type network that learns to attenuate and localize pathology-related features of a given classifier. Once trained, this network can deliver the desired attribution in a single forward pass, thereby provide faithful and informative interpretation even in real-time environments. Irrespective of the chosen method, domain-aware marginalization is a key component also in this setup for clinical applications. Image marginalization has the task to replace attributed image regions with healthy tissue in an anatomically correct way. To solve this task, we chose the unit-like architecture with partial convolution presented by Liu et al. At ECCV 2018. This network takes as input the masked image and the binarized map and yields the marginalized image as visible in the architecture figure. It utilizes partial convolution, which considers only unmasked inputs in a sliding window to compute its output. The method can handle irregular whole masks, which is important as such masks appear at the attribution training. It uses a composite loss function, which balances different components. It emphasizes local context by per pixel losses and favors globally sound anatomy by perceptual and style losses. An additional total variation component ensures smooth transition between missing and present image regions. To evaluate the suitability of the marginalization, we computed ROC curves using the classifier trained on the public mammography data. The ROC curve plots the diagnostic ability of the binary classifier. For reference, we computed the original classifier's ROC curve, which you see here in green. We then randomly replaced image regions on healthy images, which is depicted in blue. Moreover, we analyzed random replacements in pathology depicting images where replacements were made at pathological regions. This results in the red curves. Pathological tissue transforms into healthy, as visible in the red boxes of the example mammography scans from top to bottom. This experiment shows that the technique meets our demands. Significant deviation is visible only when marginalizing pathological tissue. The curves of healthy replacements follow the reference curve. Here you see visualization results on mammography data. The first column depicts ground truth annotations. The second column depicts OR attribution results. And the third and the fourth column depicts results from state-of-the-art methods called GradCam and saliency. If we compare our results to attribution maps from state-of-the-art, it is apparent that our maps are more compact and more focused around ground truth. We evaluated our method quantitatively on public mammography data. We measured Hausdorff distances and intersection over union between the ground truth and our result attributions. It turned out that we are 1.5 times closer to ground truth than state-of-the-art. Moreover, our attribution maps are 3 times compacter than the result maps of state-of-the-art GradCam and saliency. And last but not least, the execution timings are by a factor of 1.5 times faster than runtimes of state-of-the-art. This concludes our presentation. For further details, please visit us at vrvis.at.